So for this talk, we'll talk about how we orchestrated Mininet with Flask. And what is Mininet? Mininet is a network emulator that was developed at Stanford to test and emulate network traffic at an enterprise scale. They were able to emulate over 4,000 hosts and switches. And the hosts on Mininet are running the Linux kernel, and the routing and switching devices are running virtual routing and switching protocols. So how do we interact with Mininet? Mininet provides a command line interface that allows us to control and manage the network from a console. So we can ping from H2 to H3, where H2 and H3 are each host devices on our network. We can also run simple HTTP servers because they have the Linux kernel available to them. Now, this doesn't really allow us to interact directly from our web interface, but fortunately, Mininet provides an API which will expose a lot of this same functionality to us. So Mininet's API allows us to create custom networks using Python. So the API exposes several pieces of functionality. So if we look at the first two lines on the previous slide, the modules that we're importing are Mininet libraries that expose Mininet and its certain topologies to us. So on line 3, we can create a topology of depth to and fan out to, which is shown on the right, where the fan out is the number of branches from each node on the tree topology. We can start the topology. We can assign variables based off of the hosts running on the topology, and then we can run commands from those as well. So this gives us a lot of the functionality that we want to provide to our users. So our goal for this project was, slide please, to allow users to access that Mininet functionality from the user's web interface. So some of the constraints and unknowns we had were, with Docker, how are we going to be able to communicate with the containers? So previously, when it was just Mininet running on the container, we didn't have a way to actually send and receive information to Mininet. We wanted to make sure that we were validating input where appropriate for our users. So we wanted to, for instance, make sure that the topologies that we were sending to Mininet were correct and would actually allow the user to interact with it. But we didn't necessarily want to check the commands the user was running, because that would provide them with the feedback that they needed for our students if they were running an invalid command. And lastly, we also wanted to make sure that we had resource availability. We didn't want to spin up containers if there weren't going to be enough resources to support it by unnecessarily introducing latency to our total network. So for the design for this, we wanted to provide three main components for our API for Mininet. One was the topology feature. So we wanted to expose the ability to update the topology. We also wanted to expose the ability for the user to run commands. So we did that by respectively adding an API topo and an API command post endpoint for our Flask RESTful that is running on our Mininet containers. And then we also added an API terminate endpoint to free up resources when the container is no longer in use. So by exposing those endpoints on Toynet Mininet, we were able to add certain functionality to our Flask backend as well, where we could now load default topologies by interacting with our database, which stored those default topologies. And then we could also change the running topology based off of user input from the front end. And then we could also send and receive commands from the front end as well. So some of the challenges we had for our project were with Git submodules and naming. So for instance, Python doesn't allow you to import modules that have a hyphen in the name. So we had to use our submodules to rename our Toynet Mininet backend to Toynet_Mininet to expose the functionality to our Toynet Flask. We also had some issues with containerization and testing. So the Toynet Mininet was running in containers, but in order to test the API endpoints I just discussed, we needed to actually run our tests in a containerized environment as well. So what we did was we created a make file that would spin up that test environment and run through our PyTest suite that we'd written for that. So what's next for us? We're going to consolidate and refactor a lot of our code. We incurred a lot of tech debt throughout this phase that we'll be able to consolidate and make a lot of our code a lot cleaner before we open source this. And then we'll be able to optimize our container spin up. So currently we're introducing some latency manually to ensure that our containers are available to our students as soon as they start their session. And what we'll do is we'll run through some tests to find out how much time that takes to come up, and then we'll optimize it from there. And then lastly, we'll be looking at scaling this with Kubernetes to make it more accessible not only to our students, but to other people who are interested in using our platform as well. And we'll get more into that with our next talk.